Hello, my name is Dmytro Perepolkin. Today I want to present you the tenets of indirect inference in Bayesian models. We co-authored this article together with Benjamin Goodrich of Columbia University and my colleague Ullrika Sahlin here at Lund. The article has been uploaded to the OSF preprint server, and you can find the DOI and the QR code pointing to the article repository on your screen right now. The objective of our paper has been to extend the application of Bayesian inference to probability distributions defined in terms of the quantile function. We introduced the term of indirect likelihood to denote the method of inference for distributions which lack an explicit probability density function. We adopt the approach used by several researchers in the context of various quantile distributions and provide examples illustrating the equivalence of the quantile-based or indirect likelihood to the conventional density-defined or direct likelihood, also using classical models. We extend the same method to propose the definition of indirect prior and discuss the situations where it can be useful. In our paper, we consider the practical aspects of the numerical inversion of quantile functions required by the indirect likelihood method. In particular, we consider the problem of ensuring the validity of a quantile function with the help of Chebyshev polynomials, and provide useful tips and implementation of these algorithms in STAN and in R. We believe that the method of indirect likelihood can offer the scientist an opportunity of building more flexible Bayesian models based on quantile sampling distributions. Indirect prior specification can simplify the elicitation process and provide access to a wider spectrum of custom-made distributions. Our follow-up work on quantile parameterized distributions is just one example of such benefits. The supplementary material to our article contains several examples of the numerical inversion of quantile functions. The template code and an accompanying R package implementing the distributions discussed in the paper can be used by our readers in their own models. Finally, the method of quantile function validation using Chebyshev polynomials offer a novel approach to ensuring the validity of the model parameterization, which can be applied in a wide set of contexts beyond the applications discussed in the paper. Before we introduce the direct and indirect likelihood, let us revisit some of the foundations of the probability distributions and the various functions which can be used to define them. The distribution of a random variable x can be described either by the cumulative distribution function, CDF, or by its inverse, known as the quantile function. Relatively few distributions have both CDF and the QF defined analytically, while a lot more have only one of them. Some of the best known probability distributions, such as normal, log normal, and gamma distributions, do not have an analytically defined quantile function. Likewise, there are other distributions defined only in terms of their quantile function, which do not have a closed form CDF or PDF. The best known distributions of this class are generalized lambda distribution, GLD, GNK, GNH, and Govindarajulu distribution. Throughout the paper, we used the notation capital F of X to denote the CDF and capital Q of U to denote the quantile function. The derivative of the quantile function with respect to the probability U is called the quantile density function, similar to how probability density function, PDF, is the first derivative of the CDF with respect to the observable x. Where the two of these derivatives meet is at the reciprocal of the quantile density function, also known as the density quantile function. It is numerically equivalent to the PDF, except it does not integrate to 1 over the range of u. The relationship between these functions can be illustrated in the Möbius loop, where q of u and f of x would be printed on the opposite sides, while density quantile function and the PDF would meet on the same side, just rotated in relationship to each other, indicating their reciprocal relationship. You can download and print your own souvenir like that from the supplementary materials. Therefore, the main notation to remember are the CDF denoted by the capital F of x and the QF denoted by the capital Q of u. Quantile density is denoted by a small q and PDF is traditionally denoted by a small f. The quantile density is reciprocal to the density quantile, which is numerically equivalent to the PDF. Well, what implication does it all have for the Bayesian inference? For a random sample of x underscore consisting of n observations, the Bayesian inference equation can be stated as follows. F of theta, given observations, is proportional to the likelihood, here denoted as a function L, times the prior f of theta. Note that the likelihood is a function of theta and observations x. Consider a set of cumulative probabilities u underscore, which we also call depths, such as that the quantile function of these depths, u, given the parameter theta, precisely matches the observations x. We call these values depths because they indicate how deep the observations are into the distribution. Given these depths u, we could substitute the values of q underscore, which is a set of quantile functions applied to the depth u, given the parameter theta. The restated likelihood is equivalent because the resulting vector q underscore is exactly matching the observables x per our definition. So what's inside of these likelihood functions? How do we calculate them? If we look closer into the likelihood L of theta and x, the likelihood is the product of densities applied to each observation given the parameter theta. It turns out that the restated likelihood also contains the product of densities only in the quantile form, so a product of density quantile functions given the parameter theta. We call the first type of likelihood direct because the observations x underscore are used in the calculations directly. The second type of likelihood is called indirect because instead of relying on observations x, it uses the depths u, which act as intermediate degenerate random variables fully defined given the observations x and the parameter value theta. You might say, where do we get these depths u? This is where we come to the algorithm. Here, of course, we're talking about the algorithm to find the depth values u, not the piece of radioactive metal shown on the picture. For the probability distributions which have both the CDF and the quantile function, the depths u can be of course found by applying the cumulative distribution function to calculate them in a closed form. For other distributions, we can numerically estimate the depths u given theta using the inverse of the quantile function. Numerically inverting a quantile function is the same as finding the root of a function here denoted by the capital omega, given the observables x, and using the root finding algorithm, we can pull in the inverted equivalent q of u until the two values exactly meet. We do it iteratively by adjusting the depth u. There are several root-finding algorithms which have been developed over the years. We could roughly divide them into two groups, those that require two initial guess values and those that require only a single guess. The two guess values required by the bracketing methods should surround the true root value of u. By the true value, we of course mean the value of depth u corresponding to the observable x, the point where the observable and the quantile function of the depth meet, and the target function is equal to 0. In order for the root-finding algorithm to converge faster on the true value of u, it is desirable that the range u plus to u minus be small, meaning we should have a rough idea where the true value of the depth u is. The non-bracketing methods rely on a single guess value u star and the derivative of the target function omega prime, which indicates the slope of the quantile function at any given point u. The most famous of the bracketing methods, called Brent algorithm, is behind the base function uniroot in R. Stan until recently only had a non-bracketing method implementation, Powell hybrid algorithm, intended for solving large systems of linear equations. In our code example, we show how to repurpose it to invert quantile functions in Stan. Unfortunately, not every quantile function can be inverted. On this chart, you can see a quantile function and the corresponding density functions for the G and K distribution. The combination of parameters here make this quantile function invalid. The key property of a valid quantile function is that it should be non-decreasing over the whole range of 0 to 1. This quantile function decreases, although ever so slightly around the depth of 0.3, but the decrease is almost undetectable to human eye. The effect on the quantile density function is more pronounced. We see that the function touches 0 and actually goes under the x-axis for a very small interval. The reciprocal of the QDF is really showing the pronounced effect, with the two spikes indicating the two roots of the QDF. As we can see, detecting the presence of roots of the quantile density function can indicate that the slope of the quantile function might become negative, which makes the quantile function invalid. First strategy of dealing with the risk of invalid quantile function is restricting the admissible combination of parameters. In the paper, we provide several examples of distributions which specify the rules for parameters. Some of the rules may be quite complex, mutually exclusive, and nonlinear. Another strategy which works reasonably well is grid checking. If the computational costs associated with a quantile function are relatively low, we could calculate the quantile density values for a regularly spaced grid over the range 0 to 1 and see if any of them is negative. If the grid is sparse, we could miss small regions of negative values as we had in this case, but if the grid is too dense, the computational costs will add up. We could compute the global minimum of the quantile density function and see if it's negative. But given the complex shape of this quantile density at hand, the strategy looks problematic. We could also try and find roots of the quantile density function directly using one of the root-finding algorithms we discussed earlier. Unfortunately, since we don't know a priori if any of the roots exist, and in most cases we hope they don't, we cannot indicate the initial guess values close to the root, let alone bracketing the root. Finally, we could approximate the quantile density function using the Chebyshev polynomials and check for the presence of roots using the closed-form analytical solution. This method is described by John Boyd in several seminal papers dedicated to the proxy root finding. So, what does the Chebyshev polynomial approximation look like? In these graphs, you can see the quantile density function from the previous example with the Chebyshev polynomial of the order 10 fitted to it in the yellow line. The order of the polynomial can be reduced if the range is split into the smaller partitions. The chart on the right shows the same quantile density function with the range split into 10 smaller partitions. Here, the cubic polynomial seems to be sufficient and able to identify the same two roots. Some quantile density functions may be more difficult to approximate than the others. Here you can see the QDF of a GNH distribution approximated by the polynomial of the same complexity. A number of false roots are identified. Partitioning the function range just shifts these false roots to the sides, but does not eliminate them completely. These roots can be easily invalidated by checking several quantile density values between the roots to see if the density function actually goes negative in any of these regions. Checking a handful of points is definitely less expensive than computing the quantile values for a dense grid of points, especially if the calculation is relatively expensive. The accompanying R package Cupid implements the proxy root finding for an arbitrary quantile function with and without partitioning. In the beginning of our discussion, we mentioned that the principle of indirect inference can be equally applied to the prior distribution. Let's revisit this concept real quick. Assume that the prior information about the parameter theta can be summarized by an invertible function f of theta equals v, such as the inverse of it, the quantile function of v, equals the original value of theta. Then we can substitute the quantile function of v for the theta in the familiar Bayesian inference equation and get the posterior density quantile proportional to the prior density quantile times the likelihood function parameterized by the quantile transform of the random variate v. This equation is missing one important element. Because our likelihood is parameterized by a transform parameter and the transforming function is nonlinear, which is quite likely for any quantile function other than the uniform, such likelihood requires a Jacobian adjustment. A Jacobian should be equal to the absolute derivative of the transformation. In our case, it means the absolute value of the quantile density, which is the first derivative of the quantile function. Therefore, the complete Bayesian inference equation should have both the density quantile of the prior and the quantile density of it, which for any valid distribution would cancel each other out. So indirect prior can simply be expressed without the density function. The quantile transform of the random variate parameterizing the likelihood is the only indication of the shape of the prior distribution used. This formulation is known as an inverse sampling, and it constitutes a valid specification of the prior. Indirect specification of the prior can be useful in combination with quantile parameterized distributions such as Meyerson, Johnson QPD, or Metalog, since the parameters of those distributions are quite intuitive and easy to elicit. This can be very useful when parameters are specified by the experts in the form of the quantile probability pairs, such as the median and the upper and the lower quartile. Please check out the preprint repository for the full text of the article and consider reviewing it on the prereview.org platform. We value every feedback we get since it helps us improve our research. The distributions used in this article can be found in the QPD package, which you can install from GitHub. We thank you for your attention. The link to the slides is included. Please reach out to us with your comments or suggestions, and stay tuned for more videos presenting the articles from our research group. Thank you.